The next useful idea about correlation is how often it's misinterpreted. So there is a very famous statement in statistics which is correlation doesn't imply causation. Let me explain you this idea with a very simple and very nice example. And I found this example when I was trying to find out what are the right ways to teach about correlation, causation, confusion. So I found this on Stack Exchange. Stack Exchange is a brilliant resource where you can get answers for a lot of your programming and other questions. So I'm on stats.stackexchange, which is a nice place where you can post a question that you have about statistics and it gets answered very, very well. And some of the best people who can, this is like Quora, literally, for technical topics, right? So this is a very nice example from New England Journal of Medicine. And let's look at these two random variables. My first random variable, X, is chocolate consumption per capita, which means what is the average amount of chocolate consumed per person in a given country, right? So we have taken countries and we have computed my X as chocolate consumption per person per year in kilograms, right? My Y-axis is number of Nobel laureates, Nobel Prize winners per 10 million people, right? So one thing that you'll quickly notice, let's say this is my random variable Y. So if you compute rank correlation coefficient for this, you get a value which is very high, which is 0.791, right? Which is close to 0.8, a very high rank correlation coefficient. So from this, can I conclude that here, what is happening as X increases, my Y is increasing, right? But can I say that X causes Y? Can I make a statement like X causes Y? So here, as X increases, Y increases, and hence they're correlated, right? But is this conclusion that, okay, let me read it in English, right? As per capita or per person increase of chocolate in a country increases, the number of Nobel Prize winners also increase. Or in other words, as chocolate consumption increases, your country can produce more Nobel Prize winners. That's absurd. That's incorrect, right? Just because two random variables, X and Y here, are correlated with a very high rank correlation coefficient of 0.8, that doesn't necessarily mean X causes Y or Y causes X. This is a wrong conclusion. This is absolutely wrong conclusion. It's an absurd conclusion. I've taken an extreme case like this to showcase that there'll be subtle cases. For example, you must have seen lot of media publications which says, okay, if you have coffee, your chance of getting cancer is low, or if you have green tea, your chance of getting cancer is low, or if you smoke 1 cigarette a day and not 10 cigarettes a day, your chances of if you smoke 1 cigarette a day, your chances of getting cancer are lower than not smoking at all. That's like an absurd, illogical, non-scientific thing. But a lot of people, unfortunately or otherwise, especially those who are not well trained in statistics, make these causation arguments. So just because two random variables are correlated does not mean, I repeat, it does not mean that that one causes other or vice versa. It just means they're correlated. It doesn't say anything about causation. So to understand causation, there is a whole area in applied mathematics called causal models, which is a very advanced area in statistics and applied mathematics. Right? There is something called causal models, which is a very, very hot topic nowadays in machine learning, because people want to understand what causes what. It's a brilliant new area. It's been there for a while, but it's become very, very popular in the last 20 to 30 years. And this is, I think, where this is one of the great new frontiers of machine learning today. But that's a completely different topic as compared to correlation. Please never confuse correlation with causation. And this chocolate example should always stay in your mind before you make a conclusion like this.